My name is Navanga Afwa from Group 29, and I'm going to take you briefly through our project. It's called Reinforced Deep Q-Node Distillation for Bovine Respiratory Disease Detection using Multi-Strategy Learning. So we basically have keywords like bovine respiratory disease, machine learning, deep Q learning, reinforcement learning, and multi-strategy learning. To briefly go through bovine respiratory disease is basically one of the significant challenges affecting the cattle industry here in worldwide. It basically affects the respiratory system of animals, and it leads to increased treatment costs, reduced animal performance. It increases the mortality rates. One of the symptoms of bovine respiratory disease, look at reduced appetite, look at symptoms like coughing, labored breathing. For machine learning, basically, when I talk about machine learning in simple terms, okay, more of to explain it in layman's language, it's basically teaching a machine how like to work. Okay, it's basically teaching a machine how to work minus necessarily giving it the actual information it has to work with, something like that. So for deep Q learning, when I talk about deep Q learning, you're basically focusing on decision making. Then reinforcement learning, deep Q learning, it's just a type of reinforcement learning. So it also rotates around the same thing. We are basically focusing on decision making, like try and error, like try out something, then later something like that. So then for multi-strategy learning, it's basically a combination of supervised and unsupervised learning. So to go through the background and introduction, just like I've given you the definition, like the background of BRD, it's some major cattle health issue. It leads to economic losses such as mortality, high mortality rates, the treatment costs, reduced productivity, and one of our goal, the goal of this project, is to come up with an automated BRD detection system using machine learning that we basically work with sensor inputs that use features such as temperature, activity, and respiratory rate to go ahead and detect the BRD. Then the outcome, you have timely alerts that don't require the farmer to be physically at the farm, but can get immediate, like timely alerts that maybe cattle tag this is not healthy. Yeah, that's leading to improved welfare and reduced losses. So basically, this is the visual flow whereby you have the sensors, they go ahead and collect data, then push to the model, then the model goes ahead and detects, and then the farmer basically gets the alert. So this is something on related works, recent trends, and the literature review. So basically, here we are focusing on training our models to go ahead and spot the BRD signs early, but not just using the static data, but by learning dynamically from the cattle behavior. So we are highlighting the growing use of machine learning and precision livestock farming in tackling bovine respiratory disease, which is a major challenge in the cattle industry, whereby we have traditional diagnostic methods that are subjective and time consuming, which require make the farmer to be physically there to go ahead and supervise and be like, the moment maybe this cattle is behaving in such a way, it maybe indicates that it's sick. But these kind of sensors that we have, they don't require you to be there physically. They will always provide timely interventions, and then the farmer will basically get an alert and react accordingly to improve the animal health. So by integrating machine learning and precision livestock farming through advanced monitoring technologies, we guide and reduce the antibiotic use, which contributes to more sustainable and data-driven livestock management practices, which reduces dependence on subjective clinical evaluation. So, say something on the problem statement and the computational problem statement and the computational problem. Basically, just like I gave you from the definition, basically it highlights that our system, its main focus is on efficiency, faster system, and reliable. So basically, the computational problem is basically how can our system accurately go ahead and detect the BRD, putting in practice, like not forgetting the efficiency, maintaining the speed, and then being reliable. So that's our computational problem. Like basically, it involves developing binary classification model that can go ahead and distinguish health from BRD affected cattle. That's been putting in practice the efficiency and look at being faster and reliable. For the domain application problem, you're basically focusing on the computational challenge in the project. Just basically to come up with a system that can go ahead and seamlessly integrate into the farm operations, thus providing timely, actionable insights to farmers, improve animal welfare, and reduce economic losses. Some of the challenges include reliable data acquisition, scalability, farmer adoption, addressing ethical and social implications. So research questions and objectives. Some of our research questions. One is, how can machine learning models accurately detect early signs of BRD? Thus moving in line with our goals that we are mainly focusing on accuracy, efficiency, fast, and the system being reliable. What are the most significant features? Remember, basically our system rotates about the different features that the cattle possesses in terms of temperature. Is it high or low? The feeding patterns, is it consistent, or if today the cattle takes this amount, tomorrow is taking a different one? Like, how can real-time monitoring systems integrate machine learning to improve detection? You're looking at the sensors that I talked about earlier on, that like, how efficient are they? How can the real-time monitoring systems integrate machine learning to improve the detection? What is the comparative performance of supervised versus unsupervised models in BRD detection? We are basically looking at both. This is basically reinforcement learning. Just like our main focus is all about decision making. As the decision is really fast, how can how can transfer how can it transfer or deep how can transfer learning or deep learning models improve BRD detection in diverse cattle populations? We're basically focusing on generalizability in this case. Like, we're looking at the bigger picture of it, like how can our system basically go ahead and accurately and efficiently detect the BRD disease in the cattle. So some of our research contributions and outputs, we went ahead and developed a machine learning model that can go ahead and accurately classify cattle as health or being sick, which goes ahead and match with our objectives. Then we built the first real-time monitoring system that integrates machine learning algorithms for early detection of bovine respiratory disease. Then we went ahead and evaluated the performance of the developed system against existing methods. Yeah, they are there, the methods, but then our biggest, you know, advantage over them is the accuracy, sensitivity, and specificity in the BRD detection. We assessed the generalizability of the machine learning model by testing it on a diverse. We basically used a lot of data sets which are really large, which helped us to, assess like the general performance of our model, ensuring its applicability across different cattle breeds, environments, and management practices. So to conclude, with our methodology and system architecture. Basically, just like I talked about, the methods we use, that's deep Q learning, registration, and multi-strategy learning. Basically, when I talk about deep Q learning, I'm focusing on decision making. We basically teaching this model to work, like we provide some little information to it so that it recalls something, then goes ahead and applies that. Basically deep Q. Deep Q is basically all about choosing the best action based on a smart memory. So for legislation, we basically have this teacher model that we feed the data with, then it goes ahead and works with the student model. Then the student model goes ahead to use this teacher model to go ahead and detect the BRD. Then for multi-strategy, just like you hear multi-strategy, it's basically a combination of reinforcement learning and supervised learning. Then you go ahead and detect the BRD. Then basically the data pre-processing phase was critical for preparing the raw input data, ensuring the model could learn effectively. Following cleaning, the numerical features such as weight, temperature, and feeding, the milk intake, and standardization to bring all the input features to a comparable scale, which was essential for stable model training. Thanks, my colleague. We'll continue from there.
Hello, my name is John, and I'm going to start from the dataset description and exploratory data analysis. So among the dataset description, we have the attributes here and their descriptions, and the observation, the date, ID, data points, total steps, total MI, these are the movement index. and lying bouts, the number of times the animal lies down in a day, milk intake, BRD total, the temperature score, and also the temperature, and lastly the weight. So we have even more attributes than ones that are here, but these are the ones that are essential to the model. And here, among the EDA and the exploratory data analysis, we have the histograms, we have the bar graphs, we have the scatter plots. So among the output results, selected model, it had an accuracy of 92.17%, learning rate of 0.00001, training rate of 10,000, and other models performed as shown in the table. So you have the baseline model, deep Q learning model, and all these Indian model, and also the hybrid that we have, and all these performed as shown there. Go ahead to the model selection. So as shown, the selected model performed at an accuracy and precision of 92.17%, and this one was chosen because of its adaptability to changing farm conditions and low computational handling of the workload. So unlike the static models, so these are PPO-based approach land optimal intervention strategies dynamically through interaction with the environment, making it suitable for real-time periodic monitoring. So among the how we deployed, we uploaded our repository on GitHub. Then it was cloned and also dockerized, then pushed to Docker Hub. Then we deployed using render. So, and this is how the UI that we have so far is. So this is where it has the input for the dataset. After training, it gives you a comment that it has trained. Then you enter in variables. Later, you when predict button is clicked, it gives a comment here whether you should intervene or not. And a developed machine learning model for accurate BRD detection using sensor data. This was one of the limitations that we got to overcome, and also built a real-time monitoring model for early BRD alerts. So still a challenge, and achieved the high accuracy, sensitivity, specificity, outperforming existing methods, and lastly demonstrated model generalizability across diverse cattle population. So among the future works, I want to expand the data set, integrate the IoT devices like the collar that have sensors that could monitor the cattle. Also explore deep learning, develop mobile applications that could be used by farmers. And last, the recommendations with the return as for more data validation, and also focus on the cost-effective solutions for wider adoption, conduct field trials to test systems reliability in real-world conditions. Therefore, we want to extend our gratitude and acknowledgements to the institutions and authorities for facilitating resources, and also team members and collaborators for their assignment, and also to our lecturer, Mr. Kalwango. Thank you.